Section 1.5 is about inverse functions and parametric equations. Inverse functions is a review for you. Parametric equations is going to be new. Today's video is just going to cover inverse functions. So eventually you're going to have two essential questions, but today I'm just going to give you the essential question for inverse functions. So you're going to want to leave room. Describe the relationship between a function and its inverse. So the scenario is on page 35, and they give a picture, and I don't know if this is the best picture, but I'm sure we've all been on the highway or been on a road, and we've seen a crew of guys or gals, and they're basically painting the center stripe on the highway. This looks like they're doing it by hand. Nowadays, I think that they actually do it while they're driving, so guys or gals are actually sitting on the side of the truck painting. But we're going to use that scenario to explore relationships between a function and inverse. And when I talk about this relationship, I'm talking about graphically, algebraically, numerically, so using a table. Okay, so I want you to think about all of those different ways when you're thinking about describing a function and the relationship between a function and its inverse. All right, so the photograph shows a highway crew painting a center stripe. From records of previous work the crew has done, it is possible to predict how much of the stripe the crew will have painted at any time during a normal 8-hour shift. It may also be possible to tell how long the crew has been working by how much stripe has been painted. So the input for the distance, so we got the input for the distance function is time. And we also have the input for the time function is distance. Okay, so I'm going to take a couple notes here. So first of all, we're going to always assume that the crew is painting continuously. So crew paints continuously once it gets started. We're going to say that distance is going to, or D is going to represent distance. And we're going to call that in miles. That a crew paints in 8 hours. So then what would be a good variable for time? Oh, you're so smart, T, of course. So T is going to represent number of hours or time. So from that, it looks like we can come up with two different functions. We can come up with a function for distance. So our distance function, and I'm going to be real generic with this because it's going to be hard if I start throwing in crazy variables here. So our distance function is going to be f. Now, it's a function. F is a function of time. Distance is a function of time, or the input for the distance is time. So distance is a function of time. So our distance function is going to be f of t. And our other function is going to be the time function. And the input for the time function is distance. So our time function, we're going to call that g. And again, our input for that time function is distance. All right, so moving on to the inverse of a function numerically. All right, so first of all, f of t. Well, the input for f of t is the number of hours. Right, and that's what it says right here. Input for the distance function is time. What about the output? So what's the output going to be? Well, the output for this is going to be the number of miles. And so that's basically what this table is, right? Inputs are time, outputs are number of miles or distance. Well, how about for g of d then? So what are our inputs there? So our input is going to be, the input for the time function is distance. So the input here is number of miles. And the output then is number of hours. So it's interchanged, right? The inputs for the g function are here, outputs are here. That should be really familiar to you. So for example, if I want to find f of 1, well, f of 1, right, that's my distance function. Okay, that's a function of time. Plug 1 in, I get for my output the number of miles, 0.2. Okay, now let's reverse that now. Let's use the time function. So if I do g, well, my input for that is number of miles. So my input here is 0.2. And what's my output? My output is time, right, or number of hours. So I get 1. Do that one more time. Let's just pick a random one. How about f of 4? So again, the f function, okay, that's my distance function up here. You can see that. It's hard to sometimes keep these straight, so you know it's really nice to label everything so that you're able to keep this straight. So my input is time, so go down to 4, put that into the function, I get out 1.4. Okay, now let's switch that up. So now let's use the time function, whose input is number of miles. So if I put in 1.4 miles, I can figure out that the time is 4. Now this is actually really useful because, you know, a lot of construction crews, they have to give estimates. So they bid, they compete. So a lot of construction companies have to compete for their work. So they have to write up estimates and say, okay, this is how much it's going to cost us to do this, or this is how much it's going to cost whoever's asking them to do it, whether it be the government, whether it be a company, whatever it is. Okay, this is how much it's going to cost us to do it, and this is how much you have to pay us to do it. Well, in order to come up with all those numbers, they have to be able to, based on previous work, figure out a really accurate estimate. Now, what if they bid a job and then it ends up costing more to do that job? Well, they can't go back to who they actually won the bid with, who's actually hired them, and say, oh, you owe us more money. No, then their company loses money. The construction company loses money on that. So it's really important that they give accurate bids. And they want to get that bid as low as possible so that they can win, right? They want to be hired. And the reason my dad actually was, he worked in construction, and he worked in highway construction. So I remember him talking about this a lot. And he would always talk about, oh, people think math isn't important, but he uses math all the time in his job. And, part of it was physical, but also part of it was giving these estimates. Let's talk about symbols. This is also nothing new to you. So how do we label the inverse of a function? Well, inverse notation basically is f raised to the negative 1. Now, this does not actually mean, take that number and raise it to the negative 1. Okay, this is inverse notation. So this is not like take the reciprocal. It's not like the same as like 5 to the negative 1. So this is not like doing 5 to the negative 1. Okay, this is the function, the inverse of a function. And in this case, the function happens to be f. So therefore, we can say then that our time function, which we labeled as the g function, g of d, is really the inverse of the distance function, which we labeled f, or f of t. Now, how can we say that? Well, numerically, we can see that right here, right? If I put an input into this function, into the f function, I get out that. If I take that same output and put it into the g function, I get out the input from the f function. So basically what we're doing here is we're interchanging the x's and the y's, which tells me that those two are inverse functions. So I'll put since g of d is inverse of f of t. So hopefully nothing new here. Hopefully I'm not blowing your mind. Hopefully this is all a nice review for you. Moving on to the graphs. So we have the f function here, and we have the g function here. Okay, so this is my distance function. So what I can see, it looks to me like this graph starts at 0.5. Okay, so this point right here is at time like a half an hour. Well, what happened? Why didn't they start painting immediately? Well, maybe they had to get set up. Maybe they had to prepare the paint. Maybe they had to prepare all their tools. Okay, so they didn't get started right away. Okay, so then if I look at this function is my g function, right? It's the inverse, so this is my g function. Okay, so if I look at this, well, look at what's happening. So look at this point, the first point here. That point is 0, 0.5. So what you should notice, just like we did in the table, is that when you have a function and its inverse, the x's and the y's are switched, right? Okay, now let's think about this. Are these both functions? I know I've been saying function. I probably shouldn't be saying that until I make sure of it. Are they both functions? Well, this one looks to me like this is a function because, time starts at 0, so we can probably assume that, this time's just going by. They're not actually getting any distance painted, okay, until they get to half an hour. So here, what's going to happen is, they still have 0, 0. And we have all these points, 0, 0.1, 0, or sorry, 0.10. 0.20, 0.30, okay? All of those points are still here. And we'll talk more about this again, but you should recognize, well, this one's a function, this one's not. That's okay, though. This is just a relation. So it's a relationship between the inputs and outputs. And when we graph these two, so we have our original function f, we have its inverse, which is function g, then we should notice that they are reflected in this line y equals x. So anytime we're dealing with the graphs of inverses are reflected in the line y equals x. So now let's talk about the inverse of a function algebraically. We're going to do a couple of things here. A couple of things that you're pretty familiar with, I think. So first of all, I'm going to deal with the distance formula, or the distance function that we have. And that function I'm going to write as y equals 0.4x minus 0.2. Okay, so this is really, I've created it as a function of x. Okay. Now, in order to find its inverse, algebraically, what do? Hopefully you're thinking to yourself, oh, we switch the inputs and the outputs, and then we solve. Okay, so I'll go ahead and let's see, I'm going to go ahead and do it, and then I'll write out my steps. So I'm going to switch the inputs and the outputs. Okay, so we switch x and y, and then we solve for y. So my second step is going to be solve for y. So I'm going to add 0.2 to both sides. And then I'm going to have to divide by this 0.4. Okay, when I do that, I end up with, well, this really here, if I move both decimal places, I'm going to end up with 1/2. Here, if I were to move one decimal place, this would become 10. So really, I've got 10 divided by 4, which is 2.5x. Okay, so if I say that this function here is f of x, then what I've just found is the inverse function, which is f inverse of x. Okay, and again, this was my distance function, and this here is my time function, and they're inverses of each other. It gets a little bit confusing if I was to use like t and d. So instead I'm just using x. So that way I know, inputs and outputs, pretty easy to flip. Okay, and we're really used to using x and y. Now what happens if I compose these two functions? Okay, so hopefully this is familiar to you. So this was actually finding the inverse function. I'm going to kind of divide that off. Now, what about composition of these two functions? So for example, if I take f, and into that I plug the inverse of f. Okay, well, let's see. So my f function is this. Anywhere I see an x, then, I'm going to plug in my inverse. Could do 0.5 for 1/2. So I just plug that in for x, and now from that I'm going to subtract 0.2. Okay, so what I'm going to end up with here is 0.2 plus, now 0.4 times 2.5 is just going to give me x minus 0.2. Okay, oops, that should be 0.2. Notice I've got 0.2 minus 0.2, those are gone, I'm just left with x. Hopefully this is familiar to you, so that if you take a function and you plug its inverse into it, you end up getting the input out. So if I do the same thing with, let's try backwards. So now I'll take the inverse function, or the inverse relation, plug the original function into it. Okay, so what this is going to look like now is I'm going to take the inverse, which is 1/2, or 0.5. Work with all decimals. Plus 2.5 times, and now my input is going to be this, the original function. So I get 0.5 plus, well, again, that's just going to give me x, and then minus 0.5. So once again, I end up with just my input. So for example, and we can go back to our table and we can look at this. So when I had 4 being plugged in to my original function, I got 1.4 out. Well, when I took the inverse function or relation and plugged 1.4 into it, I got 4 out. Okay? Now if I take the inverse of f of 4, basically what that means, right, because that's exactly what I did here, f of 4 was 1.4. I plugged that into the inverse, and what did I get out? I got what I started, the input out, right? And so what does this mean in like real world terms? So in this situation, okay, because the original one was the original function that we had, this was distance. The inverse was the time it takes to paint a certain amount of that stripe. So this means how many hours does it take to paint the distance it can paint in 4 hours. Which is kind of silly if you really think about it, but there are truly uses for this. To make this make more sense, maybe we should say the crew. To paint the distance it can paint in 4 hours, and it's a question. All right, let's talk about one-to-one functions and invertible functions. So to be a one-to-one function, two things have to be true. So it has to be a function to begin with. And then if you were to find the inverse, that would also be a function. So in our example that we're doing, even though I've been saying function this whole time and I haven't been meaning it, right? Our original function is a function, but our other function does not pass this vertical line test, right? So we don't have just unique outputs for every single input, right? Input 0 has several outputs. So here, to be a one-to-one function, it has to be that both of them are going to end up being functions, both the original and the inverse. So we can say that every input has one and only one output, and every output has one and only one input. So basically this means that both the function and its inverse are going to be functions. Now, if this is, and I guess I should say, so if this first part is true, then that means it passes the vertical line test. And if this second part is true, that means it passes the horizontal line test. Okay, so we could even say passes vertical line and horizontal line tests. Okay, next part. If this is true, if it's a one-to-one function, then we can definitely say that it is invertible. Okay, so if it's a one-to-one function, then invertible, which again means that basically f and its inverse are both functions. So I can make functions invertible if they're not. So going back up to this one, I can make this invertible by restricting the domain. So if I say that the domain needs to be between half an hour and 8 hours, then I know that, so I restrict the time there. Then basically I would start my graph here, and this would then, every single output would have just one input. So we can make functions invertible. We can make them one-to-one, okay, by restricting the domain. So can make invertible by restricting domain. And so in our example, let me just come over here. In example above, basically we'd have to restrict our time to be in between half an hour and 8 hours. And then we're going to definitely have an invertible function. All right, example 1, dealing with inverse functions. We're given this function. Part A says to make a table of values for all of these different inputs, let's see, or outputs. So we need to input these and get out those outputs. From the numbers in the table, explain why you cannot find a unique value of x if f of x equals 2.5. And how does this result tell you that the function f is not invertible? All right, so I'm pretty sure that you guys already know how to create an input-output table. Hopefully by the time you're in pre-calculus, you know this. So I'm going to do this super quick. I'm not even going to plug it in. I'm just going to really just copy it down from the book, okay? So if I plug in -2, I get out 4. If I plug in -1, I get 2.5. Plug in 0, I get 2. Plug in 1, I get 2.5. And plug in 2, I get 4. Sorry. off the chart there. So what I can see is that there are two different inputs that give me an output of 2.5. So we cannot uniquely determine the value of x that will give us 2.5. So I can say that there are two inputs whose output are 2.5, therefore cannot uniquely determine the value of x. Plus I can see now that it's basically, if I think about the inverse here, right, the inverse, you're going to switch the inputs and the outputs. So I'm going to have two inputs, the 2.5s. This one input, that's just going to be one over here, right? 2.5, I would just have one of those, is going to go to two separate outputs. So that tells me that this right here is failing that horizontal line test. It would fail the vertical line test if we actually did the inverse and switch these. And right now it's failing the horizontal line test. So not invertible. Okay, so that's A. Okay, so B. We're going to plot the 5 points in part A on graph paper. We're going to connect the points with a smooth curve on that same axis. Plot the 5 points for the inverse relation and connect them with another smooth curve. So basically we're going to do both of these. So we're going to do the original function, and then we're also going to do the inverse relation. So a piece of graph paper. Let's see, I need a ruler. I think I'm doing way too much, but why not? All right, so for the first graph, I'm going to put, let's see, -2, 4. 2.5 is about there. 0, 2 is about here. 1, 2.5 is about there. And then 2, 4 is back up here. Okay, so I'm going to connect it with a smooth curve. Oops. This does happen to be a function, right? But notice that if I try and do the inverse, it's not going to pass that horizontal line test. So the inverse itself will not be a function, which is why they keep calling it a relation. All right, so the inverse function now, I'm just going to take each one of these points, and I'm going to switch the inputs and the outputs. So basically, I'm just flipping these around. Okay, so my input will be 4, my output will be -2. 2.5, -1. 2, 0. 1. Oh, no, 2.5, 1. And 4, 2. So that graph looks like, well, maybe a little too pointy, but that's okay. So basically it's a parabola turned on its side. How does the graph of the inverse relation confirm that the function is not invertible? Okay, so that's the part that I need to answer. So what's going on here? Well, I'm looking at this relation right here, and I'm noticing this is not a function. Why is it not a function? Well, every input doesn't have exactly one output, because it's not passing that vertical line test. So I'll say the inverse fails the vertical line test. So we know it's not a function. All right, and then C, we're going to find an equation for the inverse relation. All right, so my original function, instead of writing it as f of x, I'm going to write it as y equals 0.5 x squared plus 2. So to find the inverse, I switch the x and the y. And then I solve for y. So I'm going to subtract the 2. It might be better, instead of having this as 0.5, I'm going to write it as 1/2. It'll make my life a little bit easier. I won't have to get out my calculator to think about this. I want to get the y squared by itself, so I'm going to multiply both sides by 2. So I get 2x minus 4 equals y squared. Got to get y by itself by square rooting. So I'm going to square root and get both the positive and the negative. 2x minus 4. Okay, so that I just found the inverse. So this is actually f inverse of x. Okay. All right, so let's see what the next part of this is. We're going to plot function f and its inverse on the same screen on your grapher. Show that the two graphs are reflections of each other across the line y equals x. I mean, boy, I pretty much could do that right here. So before I go to my grapher, I'm going to show you guys that basically this function, or sorry, this relation right here, notice that it's not a function, but notice that it's got that positive output because of that plus the square root, right? So that's like a square root graph. And then it's also got the negative, so reflected across the x-axis, it's also got that negative side. So when I put this into my grapher, I actually have to put both of those equations in. So in my grapher, I would put this one as y1, that's the original function. For y2, I might put just this positive square root of 2x minus 4. For y3, I might put the, let's put the negative square root of 2x minus 4. And then for y4, I would just put that line y equals x. So I need to graph these 4 things on my grapher. But I can also show here, if I just graph the line y equals x, that's pretty good. This was f of x, and this is the inverse. Then what I can see here is that if I were to actually fold it, and you can probably do it better by yourself, but if I were to actually fold it, it actually would fold right on top of each other. Okay, so it is a reflection in this line y equals x. Make that a line. All right, and instead of taking up your time, I'm going to let you guys, I would practice this. So I would punch these into your graphing calculator as 4 different functions and make sure that you see that. Okay, you can also look in your book. So this is page 39. This is the picture that they're showing. But instead of taking up your time right now, I'll let you go ahead and do it yourself. I'm going to skip to example 4. You're given this function. You have to find an equation for the inverse of function f and explain how that equation confirms that f is an invertible function. So similar to our last problem, switch x and y. This is A. Solve for y. So what I get is y equals 1/3 x minus 4. This, in fact, is a linear function. So this is a linear function. Hopefully you recognize that. And we know that all linear functions, in fact, are functions because they pass the vertical line test, right? So we get exactly one input for every output. So it's a linear function, so it's definitely, the inverse is a function. Okay, so we can say then that f inverse of x is 1/3 x minus 4. Okay, so now moving on to B. So let's see. Why don't I go ahead? I'll just do this because I think I need this for my next one. Demonstrate that if I plug the original function in to the inverse, I get x. And then if I plug the inverse function into the original function, I get x. So I'll do this for you guys. I know that a lot of you guys already know how to do this, so you could actually just fast forward the video, try and do it yourself, and see if you can do it. All right, so I'm going to take the inverse function, which is this, and I'm going to plug in the original function. And hopefully I get x out. So I'm going to run out of room, so I'm going to go sideways here. So I'm going to get, oops, what have I done? Sorry, get rid of that. For x, I put this function in there, okay? And that's going to equal x. And then I'm going to do the reverse, so I'm going to take this function and plug it in here where I see x. I get x. Check.